almost just run through your but it's incredibly.
And we can make sure that the power is coming out of that battery pack.
How to use this new,
Sometimes the external battery
you
pack
keep getting
it likes to
stability
from it, switches to the internal one.
clear what you can do with that per. And you have to keep going back to things you've already visited and unlocking some new thing with the skill.
Okay, seems like room is still filling in, but I think we can get started. So today I'm Rishabh Maurya, and I work as a software engineer at AWS, and I recently became an open source maintainer as well. So it is my first time coming here and first time speaking in front of you all. And this project is very close to my heart, and I feel very privileged to be standing here and speaking about it. So thanks for giving me that opportunity. And I'll be presenting it with my colleague Saurabh. We have worked together on this project for several months now. And so without further ado, maybe we can get started.
Can I make a suggestion? I'm very excited about your talk, but I want to hear you. So don't be shy.
Yeah.
Raise your voice.
Yeah.
I don't know if this is microphone work.
That's a light.
And we can close the doors.
It looks like a mic. That's a light. I learned on the first day, so.
Yeah, I thought it's a mic, so yeah.
I thought so too. I just thought I'd be
It's really a bad design for a light.
Yeah, so we have a lot to cover today, so let's get started.
These people, light and mic.
So first of all, we'll be walking you through what do we mean by composability in query engines, and then what it takes to build a composable query engine, because your search engine could be a huge, gigantic monolith model. You have to break it down into modules and stuff. And then we will be also walking you through some examples, some of the very hard queries in a search engine, which is cardinality, high cardinality term aggregation. And then later on, and we'll be discussing the performance improvement which we got using this new model and the streaming allocations. And then my colleague would walk you through, Saurabh will walk you through where we stand right now. Since it's a very big project, so it's spanned through several months and years. And so he'll be discussing where we stand right now and what lies in the future. And the main idea of this talk is not to show what we have done, but also what you can take it back from this talk and implement in your own search engines or at different places. Okay, so just a quick overview of OpenSearch. It's a search engine powered by Lucy, and it's a distributed search engine, and we are kind of everywhere, as you can see: search, log analytics, security analytics, observability, vector search, ML/AI. So in order to understand composability better, I think I would like to jump back to a very old time, how the maritime industry used to operate back then. So you can see earlier in the days there would be a single terminal where a single person or a few people would be loading all type of cargoes into a ship. You can see it's a very inefficient way of handling things, because using this model the ship might be spending more time at the port than at the sea, and the loading and unloading was very labor intensive and very painfully slow. So and also if you look at it, everything is kind of jumbled together, whether it's a wheat barrel or oil barrel, everything is kind of jumbled together. There is no way of handling them in a specialized manner. But then came a revolution in the shipping industry. Everything got very fast when you have dedicated terminals for each type of cargo, and then you also have a specialized type of containers which you can use right at the truck, to the train, to the ship. So you don't have to load and unload the content inside it, but you can just ship the entire thing all the way from the factory to the destination. So this got very inefficient, and there was a revolution in the transportation and the supply chain. Now if we have to connect some dots with the search engine and how things operate over there. So basically these containers are nothing, you can assume them as a column, and the terminals are nothing but they are kind of operator within your search engine that might be doing some aggregations or joins or something like that. And they don't care about what other things are there in your payload. All they care about is what's there in that specific column, and they just want to read and process that. So you can see on the picture on the right side, how the traditional JSON-based thing would look like, how the rows are divided. But if you look at some of the advanced in-memory format or the wire format like Arrow, so there you have like record batches, and then within them you have a columnar format. So you can see things which are homogeneous, they are kind of arranged together. So this is the same thing what we want to apply in search engines as well. So basically this would minimize your serialization, deserialization cost, and also the container example which I was taking, that is something but a zero copy between different components of your search engine. For example, all the way from Lucene, where you are producing some documents or result, and then all the way to different operators on the data node, then to the wire. So you don't have to keep changing format, like using POJO, Java objects versus what you use in the memory, in-memory for processing versus what you use in the network stack. So everything could be same. And you can also interoperate. For example, if you have a very standardized format, then you can operate in a different altogether query engine. It can understand the schema and the format. So this was the motivation behind why do we need a composable query engine and how it can help. Now just to give you an overview, you can see this is a gas pipeline, and not everything you can just put inside the ship and everything would be transferred. But sometimes you need a continuous flow of things, just like in gas pipelines. And similarly, if you look at from the search engine point of view, there could be a very large data set where you want a continuous stream of flow. And this may not be applicable for all type of use cases, but it could be very helpful for some of the use cases, which we'll be discussing later on. So I think the problem is kind of well established right now. So maybe your query engine, in our case OpenSearch, was missing some of those pieces. For example, there is no standard in-memory format, and then at the transport layer we have to tweak multiple things in order to support streaming. It's very inflexible way of handling things because now each of the operator kind of is tied to a given interfaces and classes, and you can't have a generic implementation for them, so you can't port new memory format or new wire format for them. And similarly, the serialization, deserialization layer is very inflexible today, and which we are trying to modify and we'll be talking about in the later slides. And then also the data layer is kind of very tightly coupled with Lucene, which should not be the case. If you have to play around with something else and some other open source technology, then that should be pretty decoupled. And same with the language front ends and the query language. For example, right now it's very tightly coupled to the Lucene query builders, but if we have to play with something else, then it's very hard to do that. So I think in order to understand some of the examples, I'll quickly walk you through the terminology of OpenSearch, how the data is distributed in OpenSearch. So you can see we have a coordinator node and data node. So coordinator node is the one which receives a request, and it is doing most of the time very memory intensive operations. Basically it is trying to reduce all the results from different other nodes where your data lies. And data nodes kind of do very CPU and memory intensive both work, and usually the distribution look there would be one coordinator to every 10 data nodes or something like that. And there could be different scalability requirement for each of them. And then on each data node you can have multiple Lucene indexes, which is nothing but shard in OpenSearch terminology. So that is how the distribution look like. And in order to generalize some of the things and better explain things, I think operator is something which I'll be using in my talk to talk about aggregations, joins, and other things which are handling some in-memory operations within your cluster. Similarly, shard I talked about, Lucene segment, you can assume it like a mini index within your Lucene index, and I think the next couple of things like global ordinal and segment ordinals are important for this talk. So, for example, like if you have a very huge field like URL, it can have a huge payload and there could be so many documents. And when you are doing some in-memory processing with them, you may not want to load all the content in the memory. But what you can do is you can have an integer representation, just like a hash, of that particular field, right? In this case, URL. So, for example, if you have 10 unique values of URLs, then you can assign 0 to 9 to them. And then you have to probably work with integers 0 to 9 instead of complete string. So this is a very nice approach to solve some of the high cardinality use cases, and it could optimize the memory significantly. But there is a downside to it. So, so the thing is, this ordinal has to be recomputed every time there is a new segment, because now all the ordinals might change. There could be new unique values in your new segment, and yeah, so we have to rebuild it. So the way it works in OpenSearch is at the search time, if there is a change in index, you are going to recompute everything. So that is a very heavy operation because you have to load everything and then assign ordinals to them, and that would be, I mean, that would add to your first query execution time as well. Similarly, a segment ordinal is a immutable thing because segments are created, whenever the segments are created, the ordinals will never modify inside it. So it's something like Lucene already provides and is free to use. Yeah, this was important because so now I want to take one example. This example is from the ClickBench benchmark and dataset, and basically here we are trying to find the most popular URLs accessed in last several months or whatever time frame we have. So you can see like we have like 100 million document. It's a very large data set, and then there are so many unique URLs, so that means like it's a high cardinality data set. And then there are some stats around how many queries are matching, and then how many unique URLs queries matching, and so on. But the main thing which I want to explain is we have to go through some of these steps which are taken in term aggregation. And I feel like this is not just one query engine, but most of the databases might be following a similar pattern when they are doing term aggregations. So for example, in this case, like we have Lucene as a data set, so all the predicate push down happens and Lucene will do the searching for us, and then it will give you a doc set ID iterator, and you can just create a bit set out of it. After we get our doc IDs, then what we try to do is we try to search these doc IDs. I mean, we have already searched, we try to do some sort of selection logic inside them. So basically you want to fetch the way it happens today, like we make use of the global ordinals, and we try to see like how many unique global ordinals are there, and we try to calculate the sum against each of them. So that is nothing but a term aggregation, and then and since your cardinality could be very high, so the way it works specifically in OpenSearch is we try to create a top n from it. So basically, if you have so many unique ordinals, we may not want to send everything to the coordinator because it can overwhelm the coordinator. Because when we are sending the result set to the coordinator, we are actually materializing the key, and we can't just send the global ordinals because coordinator node doesn't know about what ordinals is, right? And that could differ from one data node to the other. That is not one mapping. So we have to deal at the coordinator. We have to deal with the actual URLs in this case, then the global ordinal. That is why we have to do the top n thing, and then we send it back to the coordinator. So yeah, this is the same thing which I just explained. So now let's look at like and then the coordinator would be doing the final merge and then doing a top n out of it. So now if I have to break down the performance, how it looks like today. So you can see most of the time is spent on the data node when we are doing shard level processing, and inside that, like we have few buckets where most of the time is taken. So one is the collection part itself, where we are collecting the matching doc IDs and corresponding global ordinals. And the next huge chunk is for the build aggregation part, where we are doing two operations. One is we are actually creating the buckets from the global ordinals we have created. So these are actual Java objects which we are creating. And then we try to do a top N. Basically, this top N is based on the priority queue implementation, and it will try to keep adding it to priority queue and then get the last top N from it. And then once that is done, this yellow block is about materializing the keys. Basically, whatever ordinals we have collected, we try to materialize it to the actual key and then send it back to the coordinator. And then coordinator reduce time, at least in this case, is small, so we don't have to worry about that right now. But so that was a traditional approach. So now, like we worked hard toward implementing the streaming solution. Like we have to work all the way to the network layer in the netty, and then we added a support. Like we started working toward arrow format as a wire protocol for it, and like arrow automatically support gives you a Java implementation using arrow flight. So that is what we ended up implementing, and it makes use of gRPC behind the scenes. So we get a very nice streaming model, like where you can, it gives you like all sort of streams like unidirectional, bidirectional streams, and you can make use of those constructs. So for now, like we are making use of unidirectional stream between coordinator to the data nodes in this case. So now, like once you have a streaming solution, right, now you don't have to wait for entire result set to be completed at the data node. That kind of avoids all the heavy duty stuff or in-memory state which data node has to keep. So in this case, it could be like all the URLs which we are computing, right? You have to keep them in memory or top N in the memory. And for top N, you have to keep all URLs in the unique URLs in the memory which match your query, and that could be very high. And you have to not just do it on one node, but all the data nodes. So this was one of the bottleneck, and we also saw like it's a time-taking thing computing top N. So what we thought, why don't we experiment with some of the things? For example, like we can do some sort of segment level streaming. So for each segment, after we are done with that segment, maybe we can stream it back to the coordinator. In that way, coordinator can incrementally keep reducing the result which it is getting from the data nodes, and so on. Like each data node can do the same thing, and then so in this case, as you can see, like the bigger segment would take more time and more memory, and smaller would take very less memory. So we can have some batching strategy as well, but for now we are just following segment by segment. And the very good thing about this model is we don't have to rely on global ordinals, and we have the segment ordinals already computed, and even if there is a change in index or there are new segments, you don't have to recompute the global ordinals. And this is a very nice and efficient way of streaming stuff all the way to the coordinator, and let coordinator work on the actual keys and materialize key and reduce the result. So now, yeah, as you can see, like this was kind of expected. All the memory efficiency which we got. So we got like 10x reduction in data node memory usage. And since we were not doing any top N computation, we also got some CPU gains as well on data node. So yeah, I mean, this is just, so we also make use of concurrent segment search, but all the results right now I'm showing is only for single threaded search which we are doing at the data nodes. And this is what we got, like we got some improvement in the collection time itself, because now we don't have to deal with the global ordinal based retrieval, but we are just retrieving the segment level ordinal, which we found like it's pretty fast than retrieving the global ordinal because of the nature of the data set and the smaller size of the segment versus the overall index. And also the key materialization became a new bottleneck, because across the segment there could be repeated keys, and you will be materializing them across batches, right? So there could be some overhead of that, and we found like it was quite significant in this case, and that can vary depending on your load as well, like your data set and how many URLs your query is matching and so on. As you can see, this is more of a query planning challenge, because now you have to adapt according to your query and the unique URLs which are matching, and accordingly decide whether streaming is going to help or it's going to deteriorate your problem.
Can you go back a slide? I got confused about what the change was. So you're, instead of doing it merging within the shard, you're sending per leucine segment results back. Is that right? Okay.
Yeah, we are not doing any reduce at data node at all, because and similarly in concurrent segment search we won't be making use of collection earlier and reduce logic, because we don't have to.
So there could be quite a few more than 2 segments per shard.
Yeah.
I guess.
Yeah.
You could have 20 or whatever, and
Yeah.
each one will now be returning the same amount. You're streaming more data. Right?
Yeah.
Okay.
Yeah. Right. Yeah.
And each segment has to resolve the ordinals to the labels, to the keys,
Yeah.
before it puts it on the wire.
Yeah. Exactly.
And that's the new
that's the
bottleneck, is
new
that lookup.
bottleneck, Yeah.
Got it. Okay. Thank you.
Yeah, and then I think these are the trade-offs which we wanted to discuss, and there is some we can talk in detail later on as well, but I really wanted to discuss the cardinality aggregations as well. So cardinality aggregation is like you want to find all the distinct values, not the actual value. You don't care about it, but you just want to count them. So this is a perfect streaming use case which we haven't implemented yet, but it's on our roadmap. And now, like, we make use of the hyperlog, log++ sketches, and basically data nodes have to send the full table to the coordinator in order to reduce everything and find the final count. Now we can do this step incrementally, and in a new batch you only have to send the new unique values which you have encountered, not all the hashes. So this is a very nice way, could be a nice way of handling streaming and the cardinality aggregation. Now I would like to switch it over to my colleague Saurabh, and he'll be talking in detail about where we stand right now and what lies in the future.
Hey, thank you, Rishabh. All right. Yeah, so I think whatever we have seen so far is an outcome of using Aeroflight RPC, and that's the primary benefit thing here. The reason is that is kind of the first part of the bigger picture which we thought of. We got pretty excited when we started working on the RPC, like watching Aero in flight, and we picked Mike brain on it. We did some brainstorming session, and one of the general feedback was, okay, let's realize and see like how it is actually benefiting, and that's why Rishabh kind of got ahead, and then we started using term aggregation as one of the first things. And I think the key areas where we got benefited was, of course, the memory relief, because now data node don't need to kind of pile up all those big maps or priority queues on, and then it can just keep sending the data. Now because you have less data sitting on the memory node, your garbage collection becomes more efficient, which means that data node can be more leaner. You can kind of it kind of gaps the peak memory needed for those data nodes. It also helps with scaling and isolation, because typically an open source cluster is set up with data nodes, coordinator nodes. Coordinator would be like 10% of the whole fleet, so you can make them beefier to kind of do more of the responsibility work for aggregations, versus data node can just do the fetch part of it. Also, higher throughput is, I think, we'll go more into details of it. Like I'll show some numbers and benchmarks, like how did we run around. But overall, it was about like 30 to 50% latency reduction. And one of the important aspects was it also opened the gate for us to get into the dimensions of joins, which is today not supported natively by open source. So because now you have streaming data, Arrow and there are like a bunch of other operators can come in, like maybe data fusion, which can kind of give you the ability to do those joins. So in order to establish like where we are headed with this, OpenSearch has been great for doing all of these high-level analytics and observability use cases on top of the scene. So if we take back the example what Rishabh was showing with the unique URLs that we have and then on a high cardinality data, when we try to kind of aggregate that, and if you take a very random example of maybe you have 1 million unique URLs, and then if you kind of want to build a dashboard visualization where you want to kind of go by region, and then you want to do a minutely aggregation for a 24-hour time window, and if you have like 100K unique URLs in like US West and similar URL East, so you would kind of keep accumulating those on data nodes. So now you're not doing that because you're just kind of sending it back to the coordinator, which is doing the heavy lifting, and it's kind of making it all leaner. The other advantage also is that now the real-time dashboards can start populating up super early, because now it doesn't have to wait for entire thing to kind of finish, and as soon as the data is kind of coming on the coordinator, it can be fetched by the dashboard, and your P99 latency kind of goes down. Also, if you have a particular shard which is slow, because it's very common in the open source world that one of the data node could be running under duress. So if it's a situation like that, you wouldn't have to wait for entirety of the time, but rather your dashboard can start populating with the data that is available, and then what is coming next or the last would be filling in the pieces later. So it's a lot of better experience than nothing then everything, versus you start kind of populating it much earlier. And also it also opens the gate for distributed joins, because now with metrics and traces, you would want to kind of build some combination of correlation and put some visualization on top of it. Also, it also helps with maybe if you have host level metrics like CPU and you have host level attributes, so you kind of do some on the fly joins on the coordinator. So getting into the performance side, metric side of things, so we take the same example what Rishabh was showing us. So this is the metric what we ran, enabling concurrently, like we enabled concurrent search, so that we kind of make sure that per slice is kind of dumping the results back into the queue that we have, and we wanted to kind of blast the networking, so that makes sure that we utilize the max of it, and also how much CPU is available on the coordinator and data nodes. And this is the peak performance what we see. We kind of see about like 50% reduced peak utilization of CPU between the traditional approach versus the newer approach.
I think this is very surprising to me. I don't know, maybe I'm missing something, but what is all the work that we're not doing, like in the data nodes, right?
Yeah, mostly it is like we are not doing any top end computation, so that is only coordinator.
So what confuses me is the coordinator has to do all the same work that was previously done by the data nodes, but you don't see that in these graphs, right? I mean, the coordinator has done a little more work.
Why is it not a zero-sum game?
Yeah, that's what I'm wondering.
Because like if you saw one of the earlier slides, the coordinator reduce time was very insignificant for this query. So that is why it's not evident here. Maybe for some other query it might be higher. So you are right about it. If the coordinator is doing more work, it's just that like for this query.
I mean, there's a slight blip that you see on the blue line, which is right, but it's not significantly higher. And I think it's also like spaced out, because now coordinator is doing the work continuously as long as the query is running, versus kind of waiting for the time when all the data would kind of send it like all together.
Also, if I understand your graph correctly, this coordinator is a different box with a different spec.
That's good.
With more CPUs, so if you do the work here, it's a quicker bump than if you do it over there, because the percent is.
At least in both of these graphs, the coordinator node are of the same.
Okay.
Yeah, so it's not like we distinctly put the coordinator on a heavy
I think,
node.
but this point is probably compared to the data node. Let's say if your coordinator node is 10x powerful, then I think even if there is a 2% spike from first graph to the second one, then it is like
I see what you're saying. At least in this setup, it was all uniform setup, like the same resources for data.
Does it mean latency is better?
Yes.
You're slipstreaming the computation?
Before we get into latency, I think just wanted to show on the memory side of things as well. So what you see here is, interestingly, on the left side, it's much more spiky, because whenever in the traditional way you do batching, and then when data node goes up, goes down, and coordinator asks for the next batch and things like that. Versus here, it's more streamlined and then it's more uniform. And overall, the peak utilization, and I would say not peak, but the mean utilization was 30% less. And this is the latency part, where we see that you see that initial bump in the traditional aggregation, and it's because of the global ordinals that are created like as soon as you start, and that's why you see that spike, and it kind of goes down, and it's like that's out at about 2.5 seconds. Versus in the streaming side of things, we kind of cut it down to like 250 milliseconds, or even less than that.
Do you have a question?
You were saying that you didn't chart networking there at all, but your networking traffic is going to be significantly bigger in the streaming case.
We did see that. Yeah.
But is there anything close to saturating your network?
No, not close to that. But yes,
Fat
I
pipe.
think- yeah, it was definitely higher, much higher, because now you're not reducing anything on the network. You're just
Right.
setting it.
But you have a fact, like the networking is typically very well provisioned between these boxes, right? You're not nowhere near saturating the throughput.
That's correct.
Yeah, it was around 10x for this specific query.
10x higher
Yeah,
throughput.
10x higher.
But what percentage of your bandwidth was that between these nodes?
Yeah, that is something we haven't checked. But I think it was for this specific query, we were doing like 5 queries per second. And for that, like we saw around 10 Mbps or something, because these URLs are pretty huge. So whereas in the traditional approach, it was like 1 Mbps or less than that.
Okay. But the fabric is like 100 gigabits
100
per second?
gigs, I would say, yes.
So you're like tiny drop.
Yeah, but yeah, as you increase more load, I think it's gonna deteriorate things.
Yeah. Do you think the networking would ever be the bottleneck in this?
Yeah, I think it would be both networking as well as the coordinator memory usage, because now
But
it is
networking I would doubt, because it's usually like 100 gigs or plus in the
Typically,
ecosystem.
yeah,
So it's
way
very
higher than
hard
that.
to choke networking. You would definitely choke your CPU first.
Yeah, and we also like we are using netty buffer pools, and we have ways to like control some admission control on top of it. So we can just throttle the request on the basis of how much that allocation buffer can handle. But yeah.
Yeah, I mean, one
It's
of the
definitely a
advantages,
trade-off.
what we wanted to talk about was also the bidirectional nature of these streams, which kind of makes the backdoor shipping easy, so that you don't have, I mean, in a traditional way, coordinator would ask data node and it has a timer that, oh, you need to give me before this, otherwise I'm going to fail and I'm going to reach out to another thing. But here it's more bidirectional, so whenever coordinator is done, it can let the data node that, okay, I'm ready to get the next. And so it just helps with better management of that.
And data node can stop producing if it sees there is a back pressure at the coordinator. So and we can make use of Java virtual threads or something so that we are not.
You don't have any waits happening, right? It's just a continuous
Yeah.
flow of data. Nothing is waiting
Exactly.
for the request to come back. And cool.
Yeah, so I think whatever we have seen so far has been just taking the advantage of streaming. But Arrow kind of gives you the ability to do things more in a columnar fashion, and which is something that we are yet to realize and take advantage of. So if you kind of think about that, just to kind of put the perspective, so if we had like those million log entries, Arrow would kind of put each of the field type in a contiguous memory, addresses. So for example, if you had like URLs or status field or whatever, these messages are gonna be sitting next to each other. So it just kind of makes it easier to access them instead of like chasing pointers, which is typically in a any row by row storage. Also, with modern CPUs, also love it because your caches can be presented efficiently. We have seen talks about mention of SIMD a lot in different talks, so that also comes handy because now your data is kind of lined up, so you could pick up like 8 or 16 values together in a register and process in one instruction. That's like reading a sentence instead of kind of going word by word. Also, another thing is that Arrow is language agnostic, so which means that if OpenSearch produces an Arrow data, it can be consumed by a Python client, it can be consumed by a REST library, or even Java, any application on top of it. So basically, it takes away the reason for you to serialize and deserialize the data. So it's kind of like we were talking about a quick analogy. So if let's say data was music, so it's kind of a sheet music where any musician can understand without needing a specific notation for each instrument. So it kind of also helps with zero copy interchange, so which has been also heavily realized by other open source projects like Spark, Panda, and other systems are already using it. Some of the network systems have also started adopting Arrow. So overall, I think it's kind of placing OpenSearch as a spot where it can start interfacing with other systems very easily, and it's true for other databases as well. So one of the things while we were kind of all looking into, Lucine's also started doing the block-based, Docker iteration that I think was mentioned in earlier in Ankit's talk. So this is pretty recent, and I think the whole idea is that can it provide native support for batch processing at a Lucene collector level, so that we can start using and consuming it in the aggregation framework. Very briefly to touch upon it today, it kind of goes document by document, which Ankit explained pretty well in his last data histogram presentation. So now, instead of that, we could kind of take advantage of processing things in batches instead of individual document. And of course, what we get is better cache utilization, reduced function call because it also addresses the polymorphism. You can have more inline function, and then when we have like more cleaner branching of the code, you would automatically be enabling advantages of SIMD on top of those data arrays. So in order to kind of take advantage of this columnar aspect, so which is the harder part? Like streaming, of course, was hard. It was more to deal with networking, what Rishabh was talking about. But in order to consume this columnar format, a lot of change, or I would say brainstorming, has been done, and we have been thinking about how to kind of think from the layer of the scene, the collectors, and how aggregation framework today works. So at a very high level, it's like collection of those global ordinals. Then you kind of aggregate by them. Then you do a top end. You send it back. You kind of merge on the data node. On the coordinator node. So as part of this, what you're doing is basically creating a bunch of these POJOs. You are kind of converting over the wire, and then on the coordinator, you're also doing some kind of operations to kind of merge and look into or create the process patches up finally. So if you go back to the original metric, or I would say diagram, what Rishabh showed about like the breakup of things that we have in terms of the time taken to achieve or maybe to run these aggregations. So if you look at the red line, which is the top N, is the primary thing what we have resolved right now, and that's what the one of the important aspects that is kind of giving us a lot of saving. But if you look at the build aggregation phase or the collection phase, those are the things that can actually be addressed by using the targeted columnar processing by rewriting some of the aggregation pieces that we have. And what it means is now we can replace those internal POJOs with actual arrow columnar vectors, and then which doesn't need any translation and which can directly go over the wire. The top end can use those vectorized computation to kind of efficiently do sorting or any kind of processing that we need, and then the merging or joins operation can also take advantage of like some operators that could benefit from these columnar stores. So when we think about the columnar store, I think I just kind of wanted to put this slide because it's not something very new, right? So Parquet has been the de facto columnar store for a very long time. Anybody who uses data lake, they have been probably using Parquet. And the reason it is very awesome in storage is because kind of it stores by column, it has puts similar values together, gives you better compression. It also has some metadata that kind of helps you skip some part of the chunk so that you can directly go to the part of the query that is needed. And if we historically look at if we had to kind of get a Parquet data in OpenSearch and index until all the way to the scene, a typical way would be to convert those files into JSON or CSVs, and then you hit an index API, and then it goes through the whole process of indexing. But because now if Arrow is natively supported by OpenSearch, and Arrow is nothing but a Parquet in memory, or Parquet is nothing but Arrow on disk, so it is opening the doors where OpenSearch can actually start reading the Parquet directly, and then can also treat it as an external store, or maybe a port tier or something like that. That's the landscape we are getting into. Lucene doc values have been columnar for all this while, but with Parquet, I think the interoperability and not just performance, but standardization of these interactions with different operators, or I would say even different engines, can come in very handy. So that's where the future landscape is, as Rishabh in the beginning mentioned about, that this is like a more long-term initiative that we have been thinking. We are taking baby steps to kind of see what benefit we can get from streaming, what benefit we can get from columnar, SIMD, and all of those things. So if you look about the future that's coming in, so we started work with kind of just the query to begin with. There's a lot of landscape on the query and aggregation that we need to cover. But in parallel, I think because the foundation is ready, we are kind of opening the doors for other use cases like ingestion APIs to kind of even live queries, and all of those can start using the streaming as a feature. We also are thinking that how we need to build an ability to kind of be more adaptive in the nature of decision, like what traditional versus the new streaming approach that we need to take. It could be sometimes cost-based evaluation based on the resources that are available, the cardinality of data, and basically some characteristics which can be dynamically determined. And of course, the dynamic execution, where probably you can either take advantage of SIMD, or even like in the adaptation, need to kind of fall back to the traditional approach if you are kind of regressing with the new streaming or whatever the benefits we were talking about. So this was one of the most debatable slide that we were discussing to put it here or not. But I think this kind of summarizes the whole aspect of things. Like if you look at the different layers, right from the language interfacing layer until all the way bottom left to see, is what the OpenSearch current execution engine looks like. However, the dotted box are the new pieces that we are kind of envisioning to build in with the foundation being there now. So the two important part are the columnar storage adapters. So now because Arrow is present, so you can kind of go and talk to other storage which are very natively close to Arrow in sense. And then because we are also thinking of interoperability across different engines, so maybe data fusion is one of the prominent use case which is kind of very powerful and popular for Parquet, so that can also come in handy to kind of talk to the OpenSearch execution engine and can sit in parallel for different use cases, most probably like the cold tier storage. Yeah, so I think I would just kind of want to end this with some high-level thoughts and idea. This is something we have been picking brain, both Mike, Vicky as well, about is there a direction we can think about, Arrow to be supported natively from the collector level accuracy. Maybe it would just also help in reducing translation. Of course, fetch phase kind of provides the doc values and all of that. So I think there is an opportunity there to kind of get the arrow vectors directly. And maybe for other engines like Solar, I know Solar does support streaming in some case, but it's like more like pagination and scrolling. But like there might be an opportunity to go towards like a completely streaming solution like what we are thinking right now. Yeah, so that's about it. Thank you so much. All right. Any questions? I think we have had few questions.
What issues, if any, did you encounter with the Arrow libraries, and what features would you like them to, would you want them to have that weren't already there?
Yeah, I think if I talk about the integration point of view, so there are some tightly coupled dependency, especially in the Java implementation. There are some tightly coupled dependency with Netty and Netty Commons, Netty Buffer. If you have to use the Netty based allocators, so which was kind of very tricky for us to implement, because now because we have a very extensible like pluggable model, and there could be different plugins and they might be using those dependencies, and then there would be like conflicts in them, then you might have to shadow dependencies and a bunch of other things. So maybe there could be some opportunity in interfacing them in a better way.
And just to put in perspective, I think it took about 2 months just to kind of get Arrow integrated in OpenSearch, and it was like long debate with the community about how the abstraction should be built, should we package it as a plugin, as a dependency, and I think some of those was because of the inflexibility that we had on taking that dependency on.
Yeah, and we are also thinking about like thinking from our perspective and maybe contributing it back to Apache Arrow.
Please do.
Yeah, so and
The,
there was
the current Java libraries are a bit neglected.
Yeah.
And so if you guys have stuff you can contribute back to and help, improve the Arrow Java libraries, please do, because we need it. Like, there aren't as many current active Java developers for Arrow.
Okay.
And so the more community we can get on people helping to contribute back to it, the better off that will be. Like, most of the current development focuses on, Rust, C++, Go, and whatnot. The Java ones have kind of gotten a little bit left behind.
Sure, that totally makes sense. And there was another one on the same lines, basically related to Arrow Flight.
Mm-hmm.
The basic, if you look at the flight stream API over there, that is sequential in nature. Basically, it's not observer listener spaces API. So now you have to wait for one response and then go on to the next one, and it's an iterative API.
The API, Flight allows you to send a list of locations and a list of flights that when you do the get flight info, the flight info object can have a collection of locations to send the do get to.
Yeah, in this case we just had one location, and if you have to iterate over that one stream, then you have to do it sequentially. Whereas what we wanted something like if producer is producing and producing in some random order, we can still receive it on the basis of event instead of reading it from the stream sequentially.
Interesting.
So which is something gRPC supports out of the box, and for some reason like Flight chooses not to do it in that way. And the reason could be like it is mostly used for the traditional databases use cases where it perfectly fits fine, but for some other use cases it may not be the right fit. But
I think that would be a really good thing to bring up on the dev list, dev mailing list.
Yeah, we actually saw there was already an issue open, so we thought maybe we can put some ideas how we want to.
Yeah, please do.
Yeah.
What's the next direction of travel? You had so many metaphors to start.
Yeah, I think the same thing which we were talking about, right? Like having a dedicated lane for everything and building that throughout our query engine. I think that is very important because we can't just like the way we do it is there is something called stream input and output in OpenSearch where we kind of hand roll all the response into a byte format, and each of the operator might be doing it row by row and all jumbled together. So I think that's where we want to.
That's one of the bottlenecks that we run into with backward compatibility and all, just because of this hand rolling byte buffers that we have had, like all integrated throughout the system. So I think apart from performance and the interoperability, I think just the maintenance of the code base and all of that would be elevated very significantly with this.
We're out of time now. Thank you so much.
Thank you.